Okay, konnichiwa. Hello everybody, good afternoon. Thank you for having me here today. I'm excited to be here, and I'm glad for the chance first to meet all of you, for the guys I got to speak with before this talk, and for the guys I met at the pre-event yesterday. Today's talk is going to be about a tool. Hopefully you can hear me well. It's a powerful tool. Most of us already know it pretty well. We got the introduction, so you know which tool I'm talking about. But the thing is, most of us don't think about how much we use this tool and about the importance of this tool to us. Basically, normally we use the tool, the TypeScript compiler, we use it tens of times a day. After every change we make in our code editor, as part of the CI pipeline, as part of the deployment process. So obviously it has its importance to us. And when it's running slow, it's something that can have compounding time effects on us and on the rest of the team, and obviously on the project. So today we're going to talk about tracing the TypeScript compiler. I'm going to share a bit of my experience about how I got to learn about tracing the TypeScript compiler, how I got to learn a bit more about the compiler, and that's it. So the talk is going to be split into two parts. The first part is going to be a bit more background about the compiler, a bit of general compiler theory, nothing too specific, too in-depth. But I'm going to explain how the TypeScript compiler itself is working, what it does when it's working, because normally when we run it, we just get a silent success, exit code, or just a list of errors, but it doesn't give us any information about what it did or why it took so long to complete, at least long on the bigger projects. And on the second part, I'm going to walk you through how we actually get a trace from the compiler, how we ask it to give us the trace files, and how we're going to view them. Basically, it's all very simple. All of the tools are readily available. Most of it the compiler does for us, and the viewer we have in every common browser. I know it does sound a bit overwhelming, but I do want you to stay focused regarding the compiler part. It really is quite simple. Most of you have learned it in the past and probably forgot already, but we're going to show it in a very clear demonstration and with good diagrams. So, before we get started, let me introduce myself. I'm Itai Satati. I've been developing software professionally for about a decade, and I started in a non-professional capacity almost 2 decades ago, around, I believe it was 2004, starting with Python, in the earlier versions. I've been a TypeScript enthusiast since around 2018, which is basically the first time I had a good experience with TypeScript. The compiler prevented me from making a potential production incident. I was happy, I fixed the mistake, and I started using it everywhere. And in my spare time, I love flying aircraft. I have a few types of licenses for light aircraft, the smaller ones, normally the single engine, and hopefully in the future I will get to fly larger ones. And coincidentally, actually, I started the same hobby in 2018. So it was a good year for me. Actually, before we get into that, a small side note from the conversation I had with some of you yesterday. I'm not going to get into the debate about the compiler versus transpiler. I know it's a heated debate. For the sake of this talk, we're going to reference it as a compiler, just like the official project does. And if anybody wants to discuss it later, I'll be here. So, before we get started with the explanation about the compiler, I want to tell you how I got into learning about tracing the compiler, how I got into wanting to know what it does and how it does what it does. So, I'm taking you back to last year. I was working in the same company for a few years, working on the same code base. Enjoyed it very much. But since when I started working on the code base, it was relatively small. But at that point, talking about last year, it's gotten to be very big. We got from a few developers, I believe we started as 3 developers when I joined. We got to be over 20 developers. It's a back-end project. And at that point, the company asked me to move aside and assist in a new project. A smaller one, just to help get it started, since I knew the company and the product very well. And after those few weeks which I worked on a different project, I came back to my regular code base, an experience I'm sure most of you have had in the past. And when I got to the project, I ran git pull, took all of the recent changes, a few hundreds of changes since the last time I worked on the project, and I ran the compiler. But coming there, I had all of these ideas, all of the stuff I put aside during these few weeks, just wanted to get started, and the compiler would not finish. And that's just like a metaphor. Hopefully you know the metaphor about boiling a frog, which you can't do it immediately. You must do it slowly, slowly, slowly over time so they would not notice. So I believe that's what happened to us. Basically, as developers, the project grew over time. It grew in complexity, it grew in size, and with it, the running time of the compiler also grew, and we did not know this. So by the time I came back, I said a few minutes, I believe it was between 4 and 5 minutes. I'm talking about a MacBook Pro with a new CPU, so you can only think what happens on a CI machine, which is much slower, basically on everything. So basically, after those few minutes, when I got out of the zone and basically forgot what I wanted to do at that time, I decided I'm gonna start learn a bit about the compiler. I finished the day of work and I started reading. And apparently you have very good materials in the project documentation on GitHub, but it's not too accessible. Basically, you do need a bit of background, which you're gonna get here during this talk. So, now that that's out of the way, let's get into business. We're gonna talk about the compiler. We have a diagram of basically what it does. We're gonna walk through each one of the boxes. The green ones are the phases. Basically, it's common when you talk about the TypeScript compiler's work to separate it into 5 separate phases. But before we actually get to the phases, we must start with our code. So the way that the compiler knows which code we want it to run on is using our JSConf file, which we normally just forget about. We init the project sometime a few years ago, and we change it after a few years when a new flag is added. So that JSConf file basically has an include and exclude properties. Normally they're like giant asterisks. A few of you might have modified it a bit to change the parameters. But basically these tell the compiler which files we want to run as part of the project. So we have the option to exclude the node modules. We have an option to exclude a specific file that's only used for comments and stuff like tests or stuff like that. So that's how we start. And from that, after the compiler knows which files are part of the project, we get to the first part, which is the lexer. Like I said, we have 5 phases. So the lexer is basically, if I want to simplify it, you can think about it as a tokenizer. Basically, the lexer, it gets the raw source code and it does not know anything about the code. It doesn't know about your logic. It doesn't understand any of your code. The only thing it knows is the TypeScript syntax. Basically, it knows how to take the raw string of your source code and split it into meaningful parts which will be meaningful in the next step for the compiler to continue working. So in here, I gave you an example, the simplest example you can think of, basically a variable declaration, classic one we do in TypeScript all the time. We have the const, the type of variable, the name, the type itself, which is a string, and the value, a hello world, and we can see how it's divided, like I just listed. We can also see the white spaces, which we'll talk about in a second. So the next step is the parser. The parser's role is to take all of these tokens, the blocks we got from the lexer, and turn them into an AST. What's an AST? An abstract syntax tree. Forgive me about the accent. So this tree, it's basically very similar to the simplest data structure you all learned about, a tree data structure, like we can see on the right side. It takes all of the tokens, it uses them to make some decisions about how the tree will look, but if you will look on the right side, not all of the tokens from the list are apparent over there. We can see that we ignored completely of the white spaces because they have no functionality in how our code runs. And if we had, let's say, an object declaration, an object with a few properties underneath it, here we would have the curly braces for defining the object on the left side, but when we go to the AST, to the tree itself, we will have an object, the properties beneath it, but we will also ignore the curly braces because they lose their functionality in this exact step. Normally, an AST that's generated in this step is by file, so it works file by file, and we can see on this tree, it starts at the top at the source file, goes into a variable statement. In each statement, we can technically define a few variables, so we can see it here, a variable declaration list, which only has a single item, a variable declaration, the identifier, type, and the value. This is another photo I want to share with you. This is a screenshot of basically a website you can search, TypeScript AST Viewer. There are AST viewers for every compiler imaginable online. And it helps us, if you want to play with it and understand how the AST works, it will let you just input your line of code, and I used here the same line of code just to make it easy. In the center, we have the tree that was generated, and I chose to highlight a specific node out of the tree, which is a string literal, the value itself, and we can see on the right side all of the properties on that node, whatever the compiler knows on that node. So the next step is the binder. Now I'm gonna stop for a second about the explanation. I'm gonna tell you that this is where it gets, I would say, interesting. This is where it gets to be a bit TypeScript specific. What I just described until now, the lexer and the parser are very similar to how every compiler works. Of course, they have a bit of differences, but this is in general look. The binder itself has such a big responsibility that technically I can speak only about that for the next 30 minutes. So I listed a few of its roles, but I'm only going to speak about one of them because I want to give you the proper context for the second part of the talk. And if any of you are interested, you're welcome. I will give you a ton of resources to continue learning about this, about the binder and the checker and everything else in the compiler. So the role I chose to speak about is creating the flow nodes for narrowing the evaluations in the next step. What does it mean? We have a sample piece of code here, which is an if block. We get the function gets a variable which is either a string or a number, and the if block works differently based on the type of the variable. If it's a number, it enters the first block. If not, it enters the second block. And as we can see, the end of the function is the same, regardless of what is the type of the variable. So we can see on the right side, on the flow node, I'll call it chart, basically what I just described. The start and the end are the same, but it separates. And what the binder does, it takes the AST tree, which until now didn't have any logical understanding, only syntax basically, syntax understanding, and it creates one of these. This is one of the ways that the compiler reviews our code. It does it eagerly. So basically, once we enter the binder, after we finished with the parser, it will create this kind of graphs for all of our code base, even though it might not be needed for type valuations later, just to make it, just to avoid going through the AST again in the next steps. Okay. And actually, let's talk about the next slide. So the checker. I wanted to talk to you about the next step. I wanted to actually give you a screenshot and show you something nice, but I laughed when I saw it. I figured I must put it in the slide. Basically, the checker is a single file of 3 megabytes, which all of you know is a crazy amount of, of lines of code. 53,000 as of, I believe, 2 days ago, 3 days ago, something like that. And GitHub itself does not want to show the file. So I'm going to talk about it, I'm going to explain what it does, and we're going to see just a small snippet of it. Let's see. Yeah. Okay, so I'm giving you here an example. A checker, by its name, what it does is to check. Like what we are used to get from the TypeScript compiler is a list of, if we did something wrong, we get a list of errors. Basically, it checks all of its rules, which are over 1,000 rules, and some of them are evaluated more than once. And we get a list of either rules which were broken or regular errors, regardless of TypeScript as a JavaScript language. Here is an example of a specific check, and we can see after we go through all of the checks and conditions, how it throws out the error which we eventually see in our command line in our console, basically. Yeah. So let's see. And yeah, what the checker does, it takes basically the AST, the syntax tree that was created in the parser. It takes all of the metadata from the binder, and like this function, it uses it to traverse up and down our code base, go through all of the flows in order to check all of its rules. And what I want to show, by showing that that file is large, is first to tell you that normally, when we have an issue with a compiler, it's at this stage. Basically, it has an issue, it has a type which is inefficient, not properly defined, too wide, let's call it. And when we want to help it run faster, later when we get to the tracing step, we want to think about to find the types which are causing the issues and see how we can narrow them down and make it easier for the compiler. The last step is the emitter, which is pretty self-explanatory. If we chose to emit, if we told the compiler as part of tsconfig or part of one of the flags which we passed to the compiler, we told it to emit the files, we do basically transpile. It will take the AST that was created earlier and transpile it out to JS files if we chose type declaration files and the source nodes. Okay, so this was the first step, but now before we move to the second step, I want to give you a few words about tracing, basically to make sure all of us understand what tracing means. So, tracing allows us to see action by action. It's basically, think about it like putting a log line after each action in your code. So this is what we do for the compiler. We ask it to log every single action it does with the timestamp it ran for that specific action, so we can follow through and see exactly what it did over time, and we have good tools to actually show it with clear visibility. So, what we're going to do now in the second step, we're going to pick a project since we're not all working on the same project. I picked one which should be a good reference to all of you, a relatively large one. We're going to see it in a second. Next, we're going to ask the compiler to generate some tracing files for us. I'm going to show you how it's done, how simple it is, and how quick it happens. Next, we're going to open the tracing viewer. Like I said, it's going to be in a web browser. And lastly, we're going to find the peaks in the code, technically in the viewer. We're going to go through it. I'm going to switch from the slideshow to the browser. I'm going to show you how I'm looking and searching within the viewer and what does each part of it means. So the project I chose for us is VS Code. Basically, I just cloned it this week. I'm not sure if all of you knew it, but VS Code is mostly written in TypeScript, which I was surprised to find out, and it's just an awesome fact to know. And it's the 25th most starred repository on GitHub. It took me a while to list them in a descending order. It has 180,000 stars, and obviously much more users than that, probably tens of millions, which include all of the new AI code editors, Cursor, Windsurf, Amazons, etc. So, this is how we ask the compiler to generate the trace files for us. This is I ran it within the VS Code folder. I called TSC, the TypeScript compiler, like we do every time in every project. I referenced the tsconfig file. In this project, I chose to put it in the source directory. And then I asked it for extended diagnostics. For those of you that don't know this flag, it's a really useful flag that when you add it, instead of just exiting without saying nothing in case of success, it gives us this breakdown, which I want to show you because we can see here the steps we mentioned earlier. We can see the parse time, we can see the bind time, and we can see the check time. And the check time, like I told you, it took 37 seconds, which is more than 50% of the runtime for this compilation. And again, this is on a stronger Mac, not on a CI machine, because on GitHub Actions, you can see it takes much more than that, a few minutes. Actually, let's put this aside and let me show you the files themselves. This is this one. Awesome. So, I ran the command I just showed you, and this was the output. Wait, I didn't actually. I want to go through the other one, sorry, forget about it. So, we have the generate trace flag. Generate trace flag gets a directory. We tell it where we want to get the new files, where we want them to be put. The trace file directory, in this case, I did not create it. It knows to create the directory itself. And lastly, we have incremental false. Why is it false? The difference between incremental true and false, the default, I believe, is true. Basically, when you pass it as false, it does not reuse artifacts from previous compilations, which is good for our cause because we want to get one single trace file instead of a few of them and needing to switch between them and finding the issue. We force it to recompile everything, which could be longer in this case, and normally that's what we want to do when we're deploying code. And that way we get a single file for the trace, single files for the types, like we'll see in a second. Like we can see actually on the other side, this is the output that we get in the folder, and we can view them in the browser. So let's get back to this one. So these are the two files. The first one, the trace file, the action by action log is 12 megabytes, which again is a relatively large file. What you can see inside, basically a JSON list of actions. It's not supposed to mean too much. I just want to see that it's easily approachable. You can open it, you can take a look. It's nothing scary. Basically just an array within a JSON file of action by action by action. And I think the important part is that we can see the timestamp here and just an increase in timestamp so we can understand what happened at each part of the compilation. Next is a types file. Let's see if it even opens. It's a 300 megabyte file. Basically all of the files within the project, everything, including all of the work that was done by the parser, by the binder. And in this case specifically, in VS Code, they chose to also include lots of the libraries which they are using. And that's why it got to such a big size. So we can take a look inside, basically lots and lots and lots and lots of declarations and properties. This is a bit less approachable. We can approach it if we'd like to, but I don't want to use our time on this talk for it. Yeah, so this is it. Let's see our next step. Okay, cool. Next step is open the tracing viewer. Let's just do it. So what we do, we type about, it's just Chrome, about tracing, and it opens in any Chromium browser, which basically means we have Chrome, we have Edge, we have Opera, I believe, and probably other one. I think the OpenAI new one is also Chromium. And we use load, which goes to the desktop. Let me, just a second, let's go with this one. We want to open the trace file. The demo graphs. Never mind, let's go to my backup, which I already have opened in Edge, just for this case. So basically, here if I do a load, it should suggest the file. So this is what you see when you first open the trace file. This is the first display. Let's make it like that instead of playing with the screen. So this is what we see. We see here the process ID 1, we see the main, basically main thread. In our case, TypeScript, we only work on a single thread, so we only have one of them. And we start to see the phases we spoke about earlier. Basically, we have, let me show you how to operate this. So what we have here at the top is the timeline, okay, running through the program. Inside we have all of the steps. Let's use this one. With this tool we can zoom in and out. Okay, and going like this, we can start to see, wait, sorry, I think I loaded the wrong one. Just a second. Sorry about that. Yeah, so this is the project. Makes much more sense comparing the sizes of the files we just discussed. And so this is how it looks like, a big chaotic mess. And I'm going to show you how to approach it and what to look for. So basically, we have, like I said, the timeline here above. Here now it's in seconds, not in milliseconds, which makes much more sense. And we can start to distinguish the different phases we discussed in the beginning. So we have the create program, which is basically how the first function of the compiler is called. And underneath it, it encompasses both the lexer and the parser. The green ones, which are called file source file, it opens each file and starts to process them lexer then parser and builds the AST. I believe we said that the AST works file by file. Next, we have, this is how we zoom. We use this one and just scroll. So what happens here, we have bind source file. So we can see that the next step was the binding. And lastly, we have the check source file, the checker, and we can tell that it's the longest one by a lot. Lastly, we have the emit, which in this case, since it's a very large project, also takes a while, but that's not common. Most of your projects, I believe, will not be as large in the emit stage. What we can do now, we have two options. We can, since we can see that we have very long lines on both the checker and the parser, we can choose which one of them we want to investigate. Normally, it will be easier and easier to find a win if we start to work on the checker. So I will take an example. I'm still on this one. I'm basically just scrolling to open it. But what we can tell here is that since we're working on timeline on this axis, a wider block is a longer block. So I'm going to pick one of them. Let's take the top one. And I want you to look here at the bottom. Basically, we have the duration. We see it ran for 12 milliseconds, which is a lot in this case. And once you open this view and start playing, you will see it's a lot because most of them will take less than a millisecond to run to get checked. At the bottom, we get to see the file path. We see which file was it. In this case, it's a test file. And I'm gonna share with you one of the conclusions we had in the project I worked on. We actually decided that on the CI pipeline and on the deployment, what we did is separated the compilation for the test files and for the project itself, so they could run in parallel. And actually, when we are deploying, we want to deploy faster, we did not need to compile also the test files, and that saved like 20% immediately, which was a really quick and really easy win. And we can tell it's a similar case here. I'm not sure why they chose or not chose to do anything about it, but you can tell that we have lots of work being done on the tests. I believe this one is also a test. This one is also a test. So we can see that the larger ones are tests. Let's take a look at this one. So I have more than one. And no, this is one of the regular files, which what you would do next is open the file. You have the position, basically the character within the file. You need to use your code editor to get to it because it doesn't tell you the exact line like we're used to. It gives us the position within the file, treating the new line character as just any other character because, like we said at the beginning, it doesn't know anything about the code, doesn't know any logic to it. And once you do find something, you can go to this one. Let me show you. You can go to this page. This page is part of the TypeScript project. It's called performance. Basically, if there's something about it you don't already know, not sure how to optimize, what you can do here, you can, let's say the issue is with a specific type and you're not sure what you can do about it, you can start going through them and you can see one of them is saying, here, preferring interfaces. Okay, over intersections of types. Why? I will not get into it, you can easily read, but what you will do is go through them, and what I did, other than the test files, which I explained earlier, I just went through this. It took me almost 2 hours, but in 2 hours, I got 45% optimization of the compiler running time, which went from a few minutes to, I think it was 4.5 minutes, to less than 2 minutes. And that was like the quickest way in 2 hours of work without myself knowing anything about it, about tracing and how to do it. So I just want to make sure you all understand it's super easy, it's super approachable, and that's it. Let's go through here. I believe we went through all of this. So recap, we went through the phases of the TypeScript profiler. We generated tracing files with the compiler, with a flag to the compiler. We opened the tracing file in a web browser, any Chromium web browser. We explored the tracing viewer. And lastly, we looked at some longer running types and we saw how we can try to optimize them and understand them better. Hopefully in your project it will just be easy because you would recognize them as soon as you open them. So once you do that, hopefully you have a similar experience to mine, and afterwards the compiler will no longer be an issue, which is just saying we have like a year and a half before the Go compiler is a thing, and we can start using that, and afterwards we won't have to optimize any kind of compiler work. Thank you guys.